Okay, question 2. Anushka has set up this experiment to demonstrate stationary waves using a microwave source, so a detector and a reflector. So what's happening here? We've got our source, we've got an aluminium sheet that's going to reflect the waves back, and therefore basically the sheet acts like a source that's coherent with this one because it's reflecting it. So we've got two sources, and we get a stable interference pattern that's called a stationary wave. No problem. The microwave detector is moved from left to right, and the positions of nodes and antinodes are recorded. Explain how a stationary wave is produced between the source and the aluminium sheet. So explaining how stationary waves are produced is a very standard question type in general. And what we really need to say is the microwaves are reflected. I think that's probably worth a mark. So in general, when you're answering, it doesn't really matter. Microwaves, a string, whatever. If it was a string, they would be reflected from the fixed end. That's the first point. And aluminium sheet. And then the reflected waves interfere with the incoming waves to create stationary points of constructive and destructive interference, something along those lines. Destructive brackets nodes and constructive interference. I feel like 2 marks is pretty tight for that. Yes. The position of nodes and antinodes are recorded on a piece of paper using a pencil. That is correct. Calculate the wavelength and frequency of the microwaves. So bear in mind when you get a setup like this, personally I would just draw over this with something along these lines. Oh, whoops, it's gone wrong for me. It's gone wrong. So I'm doing a kind of turn it into a wave on a string because it's just so much easier to visualize. I keep messing it up. So it's got to go through them. Maybe this is just a waste of time. It's got to go through the middle of the nodes, and it's got to go top and bottom for the antinodes, doesn't it? Like that. Brilliant. Close enough. You get the idea. And that makes it much easier to visualize that here a whole wavelength is that, not from one node to the next. A whole wavelength is the sort of double the nodal separation. So 4.9 centimeters represents 1 and a bit. I'm really sorry. What am I on about? 4.9 centimeters looks to me like 1 3/4 of a wave. I better rub that out. The mathematicians will never forgive me, will they? 7/4. How's that? Is that better? 1, 2, 3, 4, 5, 6, 7. Just checking. Yes. So therefore lambda is equal to 2.8 centimeters. Careful with the units. Frequency, we're going to use the wave equation. So we're not given any further information, but these are microwaves, so they travel at the speed of light. So just using c equals f lambda, frequency therefore c over lambda, 3 times 10 to the 8 meters per second, so do be careful, divided by 2.8 times 10 to the minus 2, turning our wavelength into meters. Gives 1.1 times 10 to the 10. Hertz, that's not very clear. Okay. Maybe 1.07. Let's go 3 sig figs. The data should lead to a value of wavelength with an uncertainty of approximately 2%. Really? Okay. Explain a very simple modification to the method that would halve the percentage uncertainty. Right, so in general, we're measuring with this ruler that has millimeters marked on it. And we're measuring 2.8 centimeters. So what we would like to do, a simple modification to the method. Notice it's to the method, not to the equipment. So I don't think we'll get any marks for saying use a better ruler or something like that. We've got to change the method that's going to halve the percentage uncertainty. So what we want to do is we wish to double the distance that we're measuring. So what we would do is, instead of measuring the distance between kind of this many, we would measure a much larger distance, something like that. A simple modification. So double the number of nodes between which we measure the distance. i.e. measure nodes twice as far apart. And obviously our resolution stays the same. So increasing the size of what we're measuring is going to halve our percentage uncertainty. Anushka is going to replace the microwave source with a loudspeaker oscillating at 12.25 kilohertz and use a microphone as the detector. Okay. Hoping that that's going to produce nodes with the same separation. Determine whether or not Anushka is correct. So this implies that the wavelength is the same. That's supposed to say true. True if wavelength same. So c equals f lambda. Lambda is equal to c over f. So 343 divided by 12.25. These are kilohertz. Equals 0.028 meters, which equals 2.8 centimeters. So yes, she is correct. Fair enough. All right.